All right, so on to part 3, we're going to talk about vapor pressure in boiling this time. So I talked last time about how when you have a liquid and it's in a closed container, it's going to reach equilibrium, it's going to condense and evaporate at the same rate, so you don't see a change in the level of the liquid. So vapor pressure is a measure of the force exerted by a gas above the liquid. So if you constantly have evaporation taking place on the surface of a liquid, you're creating a gas there. And gases exert a pressure because those particles are moving all over the place. They have higher kinetic energy, and so they are going to exert a pressure, and that pressure on the surface of a liquid is called the vapor pressure. Well, what is the vapor pressure pushing against? It's pushing against the atmosphere. In a system at constant vapor pressure, a dynamic equilibrium exists between a vapor and a liquid. The system is in equilibrium because the rate of evaporation equals the rate of condensation. This is exactly what I talked about on that last video. So if you increase the temperature of a liquid, what is that going to do? Well, more particles are going to have that minimum energy that it takes to become a gas. Well, if more particles are becoming a gas, that means you're going to have more gas at the surface, giving more pressure at the surface, and that's going to increase your vapor pressure. So all that gas, or all the liquid that's becoming a gas right at the surface of that liquid, that pressure of the gas is going to increase because you're actually getting more and more of the gas as you increase the temperature. It's going to also increase the kinetic energy of those particles. The particles in a warm liquid have increased kinetic energy, and so more of them will be able to break the intermolecular forces. So this chart shows different vapor pressures. If you notice, just look at water, don't really worry about the other ones. Well, I'll talk about them too. As you increase the temperature, notice how the vapor pressure increases. Now, one thing you'll notice, I want you to just focus in on this over here. You remember what I said atmospheric pressure was in kilopascals? It's 101.3. That's interesting. That is standard pressure at, standard temperature and pressure. But this is also the vapor pressure of water at 100 degrees Celsius. Well, what happens at 100 degrees Celsius? Water boils. So the boiling point of water is when its vapor pressure is equal to atmospheric pressure. Just hold on to that. We'll talk about it more later. Now notice these other two substances, ethanol and diethyl ether, both of them will boil faster than water, or when I say boil faster, I mean boil at a lower temperature. You'll notice how much faster their vapor pressures go up. If you are measuring it in terms of when it passes 101.3, the ethanol is going to boil before you even get to 80 degrees, and the diethyl ether will boil before you even get to 40 degrees. So you can kind of tell some of that based upon the vapor pressure. So how do we get to boiling? Well, I kind of already hinted at it, but when a liquid is heated to a temperature at which the particles throughout the liquid have enough kinetic energy to vaporize, the liquid begins to boil. Not just like the surface. So evaporation is always going to happen at the surface. But what happens when a molecule that's within the liquid, not at the surface, finally gets that minimum kinetic energy? Well, it's going to turn into a gas. So if you'll notice, when you boil something, the bubbles come from the bottom, not the top. That's because you're heating it on the bottom, and then those particles that are in the direct heat are going to get that minimum kinetic energy to turn into a gas, and when they do, it bubbles up to the top. The temperature at which the vapor pressure of the liquid is just equal to the external pressure on the liquid is the boiling point. In other words, when that pressure, the vapor pressure of a liquid, becomes equivalent to the atmospheric pressure, that substance is going to boil. That's why we saw a couple slides back that when water's vapor pressure became equal to atmospheric pressure, it boils. That's the boiling point of water. This is true for all liquids. When the vapor pressure of that liquid becomes equal to atmospheric pressure, it's going to start boiling. So that's why we've defined the boiling point as the temperature at which that vapor pressure is equal to the external pressure. Now, that does mean that the boiling point changes based upon atmospheric pressure. And yes, atmospheric pressure changes day to day. So when we say the boiling point of water is 100 degrees Celsius, we just mean at standard temperature and pressure, it's 100 degrees Celsius. On a regular day, is it 100 degrees Celsius? No, not necessarily. At a lower external pressure, the boiling point is going to decrease. Well, what does that mean? When you don't have as high of a pressure pushing down on the liquid, that means it doesn't take as much vapor pressure to overcome the atmospheric pressure. So it will boil at a lower temperature. If you have a higher pressure, the boiling point is going to increase. So yes, altitude plays a role in all of this. If you try to boil water at sea level, you'll find that you will boil at 100 degrees Celsius just like normal. If you go all the way up to the top of Mount Everest, the pressure up there is only 34 kilopascals compared to the 101.3. So it would actually boil at 70 degrees Celsius, 30 degrees lower than normal. Now, this is also true if you just go to a mountain in like Colorado or something. It will boil at a lower temperature. Water will boil at a lower temperature. This is why we have pressure cookers. Well, how does a pressure cooker work? It increases the pressure so that water will boil at higher temperatures. If you want to cook something in water at a temperature higher than 100 degrees Celsius, then you have to use a pressure cooker, and you can heat it up and the water won't boil because it's kind of like a little bomb. You have this pressure build up in the pressure cooker so that it pushes down with a greater pressure on the surface of that water. So there you go. This is just boiling point of different substances. You'll see water as you increase the temperature. Once it gets to 100 degrees, it is then equal to your standard pressure. For something like ethanoic acid, that's vinegar, it's going to be closer to 121-ish. And then, of course, we've talked about ethanol, and chloroform is even further down. So, because of the fact that boiling point changes, we have something called normal boiling point. That is the boiling point of a liquid at standard pressure, so 101.3 kilopascals or 1 atmosphere. And here's some normal boiling points. You can look those up if you ever need them. So, using atmospheric pressure, well, how do we do that? You drink out of a straw. A lot of you probably do that on a daily basis. And how that works is you create a vacuum with your mouth within the straw, and so you're lowering the pressure in your mouth in the straw, and so the atmosphere then has a greater pressure than the pressure within the straw. It's just a lot like a barometer. So when the atmosphere pushes down, it's going to push the liquid up that straw. Now, I'm sorry that I can't be with you to do this, but look up videos of these things. The can, you've probably seen this before. You heat up a little bit of water inside used soda can, and then as soon as you see the steam coming out, you turn it upside down in some cold water, and it'll crumble because you had a lot of hot gas in there, so you didn't have as many particles. And then when you cool it down, the pressure lowers a lot from what it was because the hot particles have higher pressure than the lower, and then the atmosphere crushes the can. There's also an instance of this big old tanker being crushed by the atmosphere because it is exactly the same thing as the can. But there's a video of that on YouTube. Check it out if you want to. All right, that's it for part 3.